Okay, here we are going to discuss about Zernike polynomials, and trust me, you will see Zernike polynomials a lot in your life as an optometrist, or especially you want to work in cornea and contact lens unit. So you have to deal with a lot of Zernike polynomials, especially uh, after refractive surgery, aberration or aberration due to keratoconus, pellucid marginal degeneration, or whatever. You will see a lot of uh, Zernike polynomials, and nowadays there are a lot of IOL that have been mm, discovered, done by a lot of scientists to correct the aberrations, and contact lenses custom made for aberrations. Even there are studies in spectacle that have been doing aberration control. So to reading Zernike polynomials and clinically would be very good skills for you. Okay, let's start Zernike polynomial. So it literally, the rays emerging from the actual eye are not perfectly parallel to each other, and the resulting patterns formed by the lenslet is not regular grid. So this is the first aberrometry, which is slack Hartman aberrometry. The manner in which the pattern deviates from the regular grids reveals the nature of eye's aberration, and that is quantified as a Zernike polynomials. If rays exit out from the eyes is recorded in a slack helmet aberrometry. It is no nature. It is not regular pattern, but it create the pattern that will explain how aberrated eye is. That's Zernike polynomials, second order or third order, whatever. It is now common to characterize eyes aberration in Zernike polynomial rather than the Stittle's polynomial. It's very common. Let me tell you, it's very common. Yes, definitely you need Stittle's aberrations basics, but Zernike polynomials you will see a lot of aberrometry. I will calculating instrument and everywhere in pentacam, in bone series instrument and everything. Okay, so who is Zernike? So the mathematician from were originally described in Fred Zernike in 1934, and so he got Nobel Prize for phase contrast microscopy, but he's famous for Zernike polynomials. It's quite interesting. He got Nobel Prize for another work, and he is famous for actually Zernike polynomials. So, conventional refraction breaks the wavefront down into the basic terms, which is basically spherical, cylindrical, and cylindrical axis. That's what we do, isn't it? Minus one is sphere, minus one cylinder, 890. So that's what we do. Conventional is sphere, cylinder, and axis of the cylinder. But in case of Zernike polynomials are equation which are used to fit wavefront data in three dimensions. So that's important point. Wavefront data in three dimensions. These polynomials have unique quantities. The principal one being that they decompose the shape of the wavefront into terms which describe optical aberration, such as spherical aberration. So that actually shape of the wavefront is categorized, and which describes the optical aberration in case of Zernike polynomial. So the basic terms, which is rho and theta. So basically, rho and theta, you have to understand. The rho is the normalized distance from the pupil center. So in case of Zernike polynomials, we always think Zernike polynomials in a very circular fashion. Okay, not in a rectangular or in a hexagonal fashion, because in rectangular or a hexagonal pattern we have to modify the Zernike polynomials. So rho means the distance. See in this picture, rho means distance from the center to that point where we are going to calculate aberration, and theta is the angle subtended by the imaginary line joining the pupil center to the point of intersection in a horizontal. Okay, that's the theta is angle. Okay, this rho and theta actually describes later on. So this slide, okay, so this slide, this point m and n, what is that angular frequency and radial order, that really matters. Okay, the key point here is that aberration is dependent on the pupil size. Central important, as we have discussed, is spherical aberration and coma directly proportional to the size of the pupil. Aperture is in square, isn't it? Therefore, all aberrometry measure must be related to patient's pupil diameter. So it's central important when you are sitting in the clinic and you must analyze patient's pupil diameter. Whenever you are dealing with the contact lens or you are dealing with the refractive surgery and all these things, you have to understand the pupil diameter. Okay, Wavefront measurement must be referred to as pupil size. So wavefront measurement must be measured to pupil size. If pupil size is 1 mm, then you are measuring wavefront is 6 mm. It will be false. 6 mm there are a lot of aberration. 1 mm there aberration is almost incomparably negligible, isn't it? It's 6 times lesser. So this nomenclature group has termed according to the radial order and angular frequency. I will later on show you in the picture what is angular frequency and what is radial order. So basically, if you see the Zernike polynomial 2 and 2, it means second order. This the lower one n means second order, and this means frequency is 2. And what do you mean by that? I'll tell you later. So radial order of Zernike modes in terms of rho. So rho is directly correlated to radial order, and theta is directly correlated with angular frequency. I'll tell you what is angular frequency and what is rho, okay, in the later picture. So in each Zernike polynomial there is this form. You can write in this, okay, m, and in lowercase n. The subscript n is order of the aberration, okay, and all the Zernike polynomials which n is 3 is called third order, okay. If n is 3 is third order, if n is 0 is zero order, if n is 1 is first order, okay. And okay, it's called secondary aberration. See, secondary astigmatism, the above 2 is angular frequency and below 4 is, isn't it, below 4 is, that's 4 is order, fourth order, and two frequencies. So this is the picture. So the subscription m is called angular frequency and denotes the number of time wavefront patterns repeat itself. It's central important. What do you mean by m? What do you mean by here? Let's see. In case of this 2, it 2 means 2 times same pattern repeats, okay. I'll show you in the pictures, okay. So nomenclature, there are a lot of things. See, normalized term, radial term, and angular term. There are a lot of things that happens here mathematically, which is quite complicated. So I don't want to go there. Okay. So angular frequency describes number of repeated cycles which is made over 360-degree. In one circle, how many times that pattern repeated? Okay. How many times that pattern repeated? That is m actually. N means radial order. Okay. See, this is order: zero order, first order, second order, third order, fourth order, and fifth order. Okay, the infinity order. Zero order is piston. First order, tilt in x or y axis. In these two orders, we don't consider it significant in case of clinical cases. So, as a clinician, you won't see these two orders of aberration. Actually, first and zero, 1 and 2 are all are low order aberration, and after 3 till infinity, all are high order aberration. But 0 and first, null and eins are not significant clinically. That's why only significant clinically aberration that is low order is second order aberration. Second order aberration is the aberration that we write in a prescription, isn't it? Sphere, cylinder, and the axis. So in case of low order aberration, only second order aberration is clinically significant, which is very significant because sphere, cylinder, that's what we wrote in a spectacle. That's what we correct as a spectacle. Till now, spectacle corrects only second order aberration, not this aberration, not this aberration. Okay, only second order aberration. That's what we correct from spectacle. From third order to infinity, always high order. Okay, this is low order and true low order. Sometimes you say true low order is a second order aberration, and what matters in clinic is second order aberration. Okay, from coma trefoil spherical aberration, and there are a lot of things: 6th, 7th, 8th, 9th, 10 order aberration. So zero order aberration, Zernike polynomial terms as a piston. Why it's piston? It's look like piston in front side of the piston, usually ignored. Surface is constant over the entire surface, no error or variance exists, so no significance. It's only sometimes it's called visual perception only. Okay, whatever, let it be. And this, can you see, 0 and 0. There is no cycle. So is there any pattern in 360? No. Zero order. See the first order here, minus means basically vertical and plus means basically horizontal. First order, you can see here first order, and you can see here frequency. In 360 degree, you can see only one pattern, isn't it? That's red and that's blue. That's why it's one. If it is repeated in two times, it's two. Okay, this term represents tilt and commonly seen in prisms. Okay, describe location of the image space being independent quality, and piston and tilt are not usually true optical aberration. They do not represent model of curvature of wavefront, so we don't consider it as clinically and other things. Okay, second order, can you see this pattern? One times repeated and two times repeated, isn't it? This is same, this above and this above, and repeats one time. This is one cycle and this is another cycle, isn't it? That's why here two, sorry, that's why the above is two, above is 2, here 2 is order, here is 2 which is order, but in this 360 degree is there any pattern? No, that's why it's 0. Now you're getting the concept. See, 2 is order and 2 is pattern. This is one cycle and this is another cycle, isn't it? Red blue red blue, so that's why it's 2 and 2. Second order Zernike polynomials is actually true order. It's called, it is low true order aberration. It's the only low order aberration that is very significant, and whenever we prescribe anything for patient minus 2, this minus 2 is this, and minus 1 cylinder at 90 degree, this is this, isn't it? So it's very important to understand which is which. Second order Zernike polynomial is the most significant uh, Zernike polynomial in low order, because when you talk about low order, it's null, eins, and zwei, 0, 1, and 2. Okay. Third order aberration is the first high order aberration. So I want to tell you this. Order is 3. All below is 3, 3, 3. Here is 1 because in 360 only one pattern. Red and green. Only one pattern. It's vertical, that's why it's minus. Here you can see 3, isn't it 3 pattern? 1 cycle, 2 cycle, and 3 cycle. Red, green, red, green, and red, green. That's why it's 3. Vertically minus and horizontally plus. Isn't it 3? 1 pattern, 2 pattern, and 3 patterns. So you see why it is 3 and why its lower number is 3, because it's actually order. So inner two terms are comma, because these are the comma, these are the comma, the inner two, these are the commas, yes, and these are outer two are trefoil. The name trefoil means three lips, lips. Okay, fine. So that's a third order. Fourth order, you can see fourth, four, 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 four. Fourth order mean every lower number is 4. But see, 0, there is no pattern. 2, only 2 pattern, this and this. It's 4, 1, 2, 3, and 4 pattern, isn't it? The same is here, 2 patterns. Here, cycles is 1 cycle, 2 cycle, 3 cycles, and 4 cycle. That's why it's 4. So it's called fourth order astigmatism, spherical aberration, and quadrifoil is in this picture. So 3-dimensional representation, you can find much like these pictures. This is 3-dimensional representations. It is trefoil. Again, this is same, isn't it? Vertical prism, horizontal prism, astigmatism, defocus, second order, uh, astigmatism, trefoil, comma, trefoil, and all these things. So you can see numbers and all these things. Okay. So Zernike polynomials are great interest in many fields. Optical design definitely, optical metrology, optical adaptation, ophthalmology, especially cornea field, aberrometry, isn't freeform optics. So circular pupil is the basis, and it's very important to understand. So to know the different polynomial shape and how they form and what they means actually. So disadvantage of polynomial is they cannot be used in different shape of people, like hexagonal is, they have to modify basically. Uh, so this is the picture of corneal topography by Bones series. So it's keratoconus patient. Obviously, we know the posterior surface elevated, it means keratoconus, and at the same time thinning. And if this anterior surface elevation and it's power tangential map and other things. So in this graph, bone series analysis, Bocuse Borges C number is basically depend upon aberration. Okay, so this is the graph. This is actually diagrammatic representation. This is point spread function. This is a modulation transfer function. This is simulation. But this here, okay, wait. This is low order aberration, LOA 1. This is high order aberration 0.56. And in this picture, this is, what is this? This is second order aberration. This is third order aberration. This is fourth order aberration. This is fifth order aberration. This is sixth order aberration. This is seventh order aberration. So you can see up to 7 order aberration in actually in bone series. In our hospital, that was the case. And so, what's most important is coma. In case of keratoconus, definitely. So this is another case, and I have told you that how to look at it. Okay, I want to show you one thing which is very very interesting to me. Okay, this is the patient I have done. In this case, no, is this the patient or no? This is the patient I have done the uh, scleral lens trial. See, in this case, high order aberration is 79. My goodness, it's so high. Even greater than 0.5 0.5 aberrometry is actually considered high and actually considered significant. 79, it means it's a lot. It's a lot. So I'll make one video to how to interpret the aberrometry and all these things. But 79 is a lot. And then when I put the scleral lens, after a scleral lens trial, it comes to 1.91. Still 1.91 is high, but from 79 to 1.91 with scleral lens. That's why scleral lens, we call it as a magical lens. It's really magical lens. Okay. So finally, my reference is always these three books, and that's my final book. I have used few papers from my hospital. From hospital I used to work, and there's topography maps and all these things. So I think that's it for aberration. I'll see you next video on other topics, maybe in optics. So for now, aberration is quite done, and I recommend you this book is strongly, very strongly, Geometrical Optics from Professor Dr. George Similis. Okay, bis dann, tschüss.